So I think we can get started. It's my great pleasure today to introduce our seminar speaker, Kristina Nyland. So she got her PhD at New Mexico Tech in the town of Socorro, working kind of like both at NMT and at NREO, which is where the BLA is hosted. So that makes a lot of sense. She's like a super radio guru. So after that, she went off to work at ASTR, I think, right, in the Netherlands, doing things with LOFAR, which is another long wavelength radio telescope. Before she came back to NREO, but this time at Charlottesville. And from there, she went and did a position at the Naval Research Lab, where she then became like a staff scientist kind of person there. And then just recently has swapped from NRL to stay in the DC area, but now at the US Naval Observatory. So she's going to tell us a lot about AGN. And I don't know if you're going to talk about how they're useful for like the reference frame and stuff, like that's what you're kind of in charge of now? Or if you're going to focus just like the science of AGN?
I'll leave it. I don't want to spoil it.
Okay, I guess we'll learn. So yeah, take it away, Kristina.
Well, thank you very much for the introduction and for the invitation. I've had a lot of fun talking with many of you today, and I'm really happy to be here. First, just to check, can everyone hear me okay? Well, as Justin said, I'm based at the US Naval Observatory in Washington, DC. And so you'll be mostly hearing about radio AGN and all the cool science we do with them. But I'll mention a little bit about their practical uses. And if anyone has more questions about it and would like to know more, I'd be happy to go into as much detail as you would like to hear. All right, so today, the focus of this talk really is giving you a tour of some of the recent research I've been doing to better understand the dynamic lives of radioactive galactic nuclei. So here's my outline. I'll get started by telling you a little bit about what radio AGN are and why they're important. I'll then talk about the importance of the early stages of radio AGN evolution when jets are young and compact. Then talk about some strategies for finding young jets. Turns out they're kind of elusive, with a particular focus on ways to find them in this era of surveys, radio surveys, especially that we have now. We'll then talk about some new insights that we've gained from using radio surveys to explore the life cycles of AGN jets. And I'll then, depending how much time is left, talk a little bit about some future directions, including new surveys and possibly some new telescopes. Okay, so today I've learned that this is a very extragalactic focused crowd, and so I'm glad I don't have too much introduction here. But just for completeness, this talk is about active galactic nuclei, or AGN. So these are actively accreting or feeding supermassive black holes weighing millions to billions of solar masses that live in the centers of, we think, most massive galaxies. So I chose a very famous AGN here. This is Centaurus A. In the leftmost panel, this is an optical image where you can see it's the host galaxy. It has this prominent dust lane here. This is a fairly low luminosity AGN. It's not particularly efficient in its accretion. It's a pretty low mass accretion rate. But about 10% of galaxies can be classified as AGN at some level. Now, a much smaller subset of these AGN are special in that they have bright radio emission. And so here's a beautiful example here of Centaurus A in optical, 1.4 gigahertz emission from the ATCA, the Australia Telescope Compact Array. So this is a really spectacular image here. This spans several arc minutes, or about 500 kiloparsecs. And then on the right here, this is optical plus radio and X-ray. This is C-band, about 5 gigahertz. And so it really focuses more on the radio emission that's closer to the core and more actively being fueled. Okay, so that's just a brief introduction of Centaurus A. On the physics side of things, supermassive black hole jets that we see in the radio, these are produced by a process called synchrotron emission, which consists of electrons that accelerate to nearly the speed of light, very close to supermassive black holes. So how do we observe radio AGN? This is Centaurus A here, another very famous, sorry, this is Hercules A, another very famous radio galaxy. And we use a technique to image the radio emission from sources like this called interferometry. And so in interferometry, we actually multiply the signals from a series of antennas. This is a cute cartoon of a single baseline. Up here, this is a picture of a telescope that I use quite extensively called the Very Large Array. This telescope is based out in New Mexico, and it's, I consider it the world's most powerful radio telescope since it offers a wide range of frequencies. It can probe a variety of different angular resolutions since these individual antennas can actually move along railroad tracks. So that's the Very Large Array, my favorite telescope. Another telescope that I use a lot for studying radio AGN is the Very Long Baseline Array. There's a schematic of it here. And in this case, the dishes are spread much farther apart than for the VLA. They're spread across continents, and so they can reach milli-arc-second resolution. So together, these are two US instruments that really provide extensive information for us on the physics of radio AGN. All right, so a little bit more on why AGN are important. So they're important in multiple ways, it turns out. So the first one I'll mention to you are some societal importances. So if you're, is anyone a radio astronomer in here? I know there are a few of you lurking in the crowd. So if you're a radio astronomer, you know that calibrators are really important. So like knowing which radio AGN are compact is going to be essential if you want to do anything else in the radio, whether it's studying supernova remnants or studying radio stars or anything else. Now the other thing I have up here is navigation and timing. So it turns out that all of our modern technology, including things like GPS, which powers Google Maps on your phone that you might use on a daily basis or a regular basis, all of this is really underpinned by something known as the International Celestial Reference Framework, or ICRF. This is a sky map showing the positions of the 4,000 or so distant radio AGN that comprise the ICRF. And here's a VLBA image of one of them. This little scale by here, if you can't see it, is 5 milliarc seconds. So they're quite compact. And essentially, these sources are used as the most distant beacons in the universe for determining the precise location of the Earth in space and time. And so, really important. And this is sort of an illustration of why my job exists, why we have radio astronomers supporting US Naval Observatory. It's because that radio AGN and VLBI or radio interferometry in general experience really helps support this. And if you want to know more about what I'm doing specifically at the end, I'll tell you a bit more about that. So another reason that radio AGN are important is because they probe extreme physics that we can't study any other way, especially not in a laboratory on Earth. So they probe things like supermassive black hole accretion, gravitational waves, and cosmology. I've got a few cutouts here of a very famous AGN that many of you have probably heard of. This is M87. And so it's like a scale of 1 million, a factor of 1 million in spatial scale. Different observations here taken with LOFAR, the VLBA, and then the Event Horizon Telescope. Anyway, the last thing I wanted to mention was galaxy evolution. So I started out my interest in AGN from the perspective of studying galaxies as a grad student. And so AGN are thought to be really important for galaxy evolution. They generate energetic feedback. These are some examples of energetic feedback in action. These are maps showing radio in pink and X-ray emission in blue. Except this one, sorry, the radio emission's flipped in this one, I guess it's red. But anyway, these are examples of lobes that have carved out cavities or bubbles in the hot gas intercluster medium surrounding the galaxy. These are just examples of feedback in action. And then, of course, if you are interested in the high redshift universe, AGN are believed to have helped reionize the universe. And so they are very important for many reasons. Okay. So I want to focus in on my specific interest in radio AGN. So this is a map showing the cosmic history of the universe. So the Big Bang is on the left, and the present day is on the right. Here I've zoomed in on this is Hercules A that I showed a little bit earlier. That has these really huge jets, several hundred kiloparsecs long. And I would argue that we've for decades been studying the brightest radio AGN in the sky, like this source. And we actually know quite a bit about their physics. And we understand also how they generate feedback that influences their surroundings. So they're thought to heat gas in the intercluster medium, and that prevents it from then cooling and being accreted onto galaxies to form stars. So we know quite a bit about that. But what we don't know as much about is what happens when the jets are very small and still confined within their host galaxies. So this is a really interesting part of radio AGN evolution, because when you have jets confined on ISM scales, there's a lot of potential for things like feedback and outflows, and that finding systems where we can observe that in action can really help us understand how galaxies and supermassive black holes co-evolve. So how do jets influence galaxy evolution when they are young and compact? Okay, so let's move on to the next section, the importance of the early stages. So I think I already made this point on the last slide. I'll just make one additional point that in cosmological simulations, I have yet to see a study that actually incorporates like realistic feedback that can predict instances of jet ISM feedback, like from the ground up. If anyone knows of any, let me know. Basically asking for subgrid physics here, but anyway, until we get there, we study jet ISM feedback with simulations in other ways. This is a nice example of a relativistic MHD simulation done by my colleague Dipanjan Mukherjee. He has a really nice review article that came out just in 2025, by the way, that I highly recommend. But in this graphic here, what he did is he started with an initial gas density, and then he had two different jets with two different powers. And so on the left here, this is the lower power jet, and this simulation ran for 3 megayears. And on the right here, this is the factor of 10 more powerful jet. And this simulation on the panel on this side only represents 0.79 megayears. So basically, the high power jet just kind of drills through the ISM, whereas the lower power jet, it's much slower to make it through surrounding gas. It also stirs things up quite a bit. Morphology also kind of a little bit less collimated. And so the point here is that low power jets or jets that are young and expanding into a dense ISM, they have the potential to impact the ISM, and perhaps even more so than the most powerful sources that we know more about. So here's an example, an observational example of jet driven feedback on ISM scales. I'll say this example is a bit of an older one. It's the source that I worked on as part of my PhD project, and there are tons of cool jet ISM feedback papers that have come out since then. I had trouble choosing a new one, so I stuck with this for now. This is NGC 1266. It has this kiloparsec scale radio structure, which I think is a jet. It has associated VLBA, very long baseline array emission with it, and some other lines of evidence, including radio spectrum and also polarization properties that support that. But anyway, the cool thing about this source is that it was discovered to have this outflow first found in molecular gas. So this is a CO 2:1 profile from Karma. So it was discovered by Katie Alatalo, and she identified this excess emission in the wings here as being an outflow. And it was then found to also have outflow components in atomic gas. So here's the H1 absorption data that I worked on as a grad student. And so you can see there's this very clear blue shifted component, and that is an unambiguous identifier of an outflow, since the radio source has to be behind the gas. It also has evidence for ionized outflows as well. So we believe it does happen, and we're getting more and more examples of these things. Okay, so I hope I've convinced you that young and compact jets are important and really interesting. So let's talk a bit more about some of their observational properties so we can try to find more of them. So on the left here, this is a diagram, a cartoon diagram that I made that shows how the luminosity or radio power changes as it grows, basically. So the source starts out on the left here as small and compact. Sources tend to brighten until they reach a kiloparsec or so. Then the energy loss, the dominant energy loss is changed a little bit. It gets out of its predominant adiabatic mode. As the source expands, it fades a little. And so this is an example of an old AGN. It's a little bit exaggerated since it's a cartoon, but the thing to remember is that young jets, they brighten until they reach kiloparsec scales. And so finding sources that are very, very slowly rising can be one clue. The other part, the other feature that I want to highlight is the spectral. It's a figure showing the flux density versus the frequency. And on this side, the young jet starts off over here on the right. So sources start off having these peaked spectral shapes. And this peak occurs because of absorption, often synchrotron self-absorption, which is caused by a very high number density of emitting electrons. Causes the source to essentially be optically thick. And as the source expands, so it brightens a little bit, like I told you in my last panel here. But the key thing in this plot is you can see the peak frequency is shifting to lower frequencies. And so, this tells us that there are some time domain, there's some time domain behavior, and also some spectral behavior that we might be able to use to identify young sources. All right, so in addition to spectral shape and variability, if you can directly observe a compact morphology, that's the most direct method. If we had infinite time with telescopes like the VLBA, we could just observe all the AGN and look to see if they have compact radio structures. Unfortunately, that would be too expensive. It would be infeasible. But here's an example of a source. We have such high resolution data. This is a pretty well-known source. It has like a phone number type name. It's not particularly nearby. But when you look at it on milliarc second scales, you see it has a number of components labeled here in this 8.4 gigahertz map. So if you have a redshift, that you can immediately get size constraint, and that can be an initial clue that this source could potentially be young. Another cool thing that you can do with the VLBA is you can actually observe over time and see how blobs like this are changing in their positions. So these proper motions, results of a proper motion study over here that spanned, let's see, about 12 years. You can see the different components are moving, and it's possible to actually get like a kinematic age, like a distance equals wave times time measurement. So this particular source is only 1,000 years old. So here's an example of starting with information from spectra, using that as a pre-selection. So this is a source I recently, I forgot to update this. This is now published. But this is a source that I had initially found while I was working at NRL with a commensal instrument known as VLIGHT. This is it's called the VLA low band ionosphere transient experiment. It's this piggyback system that operates on the VLA at lower frequency. And if you have PI observations with the VLA, you can request these observations by contacting the NRL project scientist, Tracy Clark. And if you Google VLIGHT, you can find NRAO's page that has all the contact information. It's really useful for things like spectral modeling for brighter sources. So here's this VLIGHT data point right here. I had initially flagged this as interesting in VLIGHT because it was it exhibited some moderate but possibly significant variability. So I said to myself, what does the spectrum look like? So I retrieved a number of data points from a variety of wide field radio surveys. Some of these might be familiar to you if you've worked with radio survey data before, like NVSS, the NRAO VLA, Sky Survey. Actually, really important. The last VLA Sky Survey, which we'll hear more about. If anyone wants to know more about them, I can tell you more. But for now, all you need to know is they're different surveys at different frequencies. And we were able to model the spectral shape of the emission with a synchrotron self-absorption model. And then we're able to follow up with the VLBA, confirm it's indeed compact. And it just so happens to be a really interesting type of young and compact AGN. It's a compact symmetric object, or CSO. And these are cool because they're in the plane of the sky and not affected by any relativistic beaming. And so we were able to do a fun study considering different possible origin scenarios, like a transient accretion event for the source in this paper. So that was just kind of a fun aside. Before I get into what I really want to talk to you about in a couple slides here, I do want to just mention a bit more about variability. So the idea of taking measurements across historical radio observation or radio telescope survey data sets has been around for a while. In 2020, there was this very nice paper done that identified a source that had some interesting spectral changes from 2016 to 2019 that were possibly related to a change in supermassive black hole accretion, so possibly a changing state-like source. You can see the real thing that makes this different than like a blazar or something that also might have spectral variability is you can see it was undetected in first government there, and it's quite a significant discrepancy. And so this is interesting. This was some work that was done in parallel to a similar study that I did here that I'll be showing you more about. All right, so let's talk about some specific tools we can use in the era of surveys. I mentioned I would tell you more about VLAS, or the VLA Sky Survey. So has anyone here used data from VLAS before? I think a few have. So, okay, fairly popular in this crowd. So VLAS, if you're not familiar, it's mapping the entire sky visible from New Mexico. It's about 80% of the total sky. And it's doing that 3 times in 7 years at 3 gigahertz. And the resolution for such a wide field survey is unprecedented. It's 2.5 arc seconds resolution. Also, it's a factor of 2 higher than FIRST, if you've heard of that one. I also want to highlight, like I said, let me explain this graphic first. So this graphic here, this is a map of the sky, of course. And it's just, the colors are just showing the different configurations that were used. So in orange, this was the VLA's B configuration. Down here, they had to use this thing called, they use B North A to get to more southern declinations. To keep the synthesized beam from being too elongated. And down here in blue, this is below the observing limit of -40 degrees. Now, one thing you might not have heard about is that there's a bonus half epoch. Bonus epoch 4.1 is completed yesterday, I believe. And so all of the rough so-called quick look image data products should be available from NRAO soon if anyone wants to explore that. You can, if you want to read more about Epoch 4.1, there's a VLAS white paper that I wrote a couple years ago about it. So VLAS has done a lot of really cool things. I don't want to spend much time on this. You can check out the white paper to learn more, but yeah, I think from stellar explosions to tidal disruption events, newborn jets, a lot of topics here that interest a lot of you in this room. If anyone here is interested in using VLAS, I just want to point out that there is a really helpful website here that was just recently updated. And this is where you can go to find guides on different data products. If you go to this website and scroll down from what I'm showing here, there's a link to an interactive HIPS viewer, sky coverage. There are some examples. You can find examples of VO queries. This is if you want to read the paper on the survey, it's right here, Lacey et al. 2020. I also included a link to some user-contributed tools. So one unfortunate thing that I should highlight is there is no cutout server at the moment, but you can visit, it's explained in the website here, you can visit the CADC and still get tiles, or you can, there's some examples of how to get cutouts with Python and some tutorial notebooks here. All right, so let's talk about some interesting science with VLAS that I've worked on. So I had this idea back in 2019 to compare VLAS and FIRST to look for, to try to find very young radio AGN. And so here's just a quick comparison of the sky coverage of VLAS at FIRST. So VLAS covers 80% of the sky. FIRST in purple is more limited. The comparison of the two surveys, they're similar in resolution, they're similar in frequency, similar in resolution, but a really key thing to focus on here are the dates. So FIRST was observed 15 to 20 years ago, and VLAS Epoch 1 started in 2017. It went from 2017 to 2019, and then Epoch 4.1 has just completed now in 2026. And this should actually say 4 asterisks or something. It's 3 and a half. We couldn't get the second half of it if we wanted to. So if you do like a simple cross match between just one of the VLAS epochs and FIRST, you find there are hundreds of thousands of sources that overlap, and there are thousands of VLAS sources that are not in FIRST. A lot of those sources are bogus. There are a lot of artifacts in the VLAS, these so-called quick look images that I mentioned, that it's prioritized to get them out quickly, which I think is a good decision overall. But yeah, kind of a user beware thing. You need to fish out the bogus sources. But once you do, you find that there are lots of really genuinely interesting objects that include things like slow radio transients, like tidal disruption events, gamma ray bursts, supernova remnants. And then there are also radio variables that are predominantly AGN and quasars. I don't want to take too much time on this slide, but I want to tell you a bit about the selection criteria that we applied after this. To get a sample of candidate newborn jets. So we started with a couple thousand variable sources over a portion of the VLAS epoch 1 and first overlap, a few thousand square degrees. And this is an example of a source that was not detected in first, and it was not because it was like 5 sigma instead of the 7 sigma cutoff of the first catalog. There really is nothing there. And then this is the detection in VLAS 20 years later. We took that list of a couple thousand sources. We cross-matched with some quasar catalogs in the optical and infrared, SDSS and WISE. And we then applied a flux cutoff so that we could weed out sources that were optically thick but not variable. So there's a cutoff on the spectral index of plus 2.5 for how optically thick a source can be. And so this is our sky map showing the 26 newly radiolog quasars that we found. So here are some very nice decals cutouts of the sample. I think I saw a decals hat in the discussion room earlier, so I think some people here must work on it.
Where did that come from?
There are, this is a nice summary of their properties. They span a range of redshifts from redshift 0.2 to 3.2. They tend to be powerful quasars. Their luminosities are 10 to the 45 to 10 to the 40, almost 10 to the 47 inverse per second. And their black holes tend to be massive when 10 to the 8 and up. So here are some plots showing the radio variability. This is just variability amplitude. So here I'm showing on the left how they varied at L-band when we followed them up. And that's in comparison to the first data. So some of them are limits because they were just completely not detected in first. Some are not limits, and that's because we went back to the original first images, and we found there were some that were significant detections, like 4 to 5 sigma, but probably real because we knew about the VLAS measurement, even though they weren't in the catalogs originally for first. So you can see the variability, it gets pretty extreme, up to 2,500% for the most extreme one. At S-band, this is the band VLAS operates in, the variability is a little more moderate. That's mainly because we're looking over months instead of years in the time between VLAS and our follow-up. But yeah, still pretty significant variability, averaging almost 20%. Okay, so here are a whole bunch of radio spectra. So as I kind of alluded to in the last slide, we did follow them up with the VLA after our initial selection. And I was very delighted to find that they all have peak spectral shapes that indicate there's very clearly absorption happening and really raises the potential that they might be a very young system. And this is a radio color plot, I like to call it. So this is showing the optically thin on the to the right of the peak, and then the optically thick. This is the part to the left of the peak. Spectral indices, and so the different quadrants basically tell you the shape. So I'm just showing here that you can see they're all consistent with being peaked systems. This line here, this is just a threshold that has been used in the literature, but mainly to accommodate error bars. All right, I'm going to skip the origin of the absorption for the moment. Let me tell you about the multi-epoch radio spectra. So we did submit initial multi-band follow-up that I just showed you. And we have a second epoch of multi-band VLA follow-up that we did to see if the spectral shapes were changing. So a changing spectral shape, depending on how it's changing, can give you some important clues. For instance, this source in the center here, you can see this spectral shape is changing, but only in the optically thick part. And this is actually what you like textbook adiabatic expansion of the young jet. So that was exciting to see for some of the sources. The timeline between the time between observations is only a little over. It's between 1 and 2 years, depending on when the observations took place. But what we really need is a little bit of a longer time scale to really characterize, really get some more physics with it. Hoping maybe the next age-phase cycle for some more time. There are also some sources like this where the spectral shape changed a lot, and in some cases, in particular, from 2019 to 2021, the spectral went higher frequency, which is not what you would expect for an expanding source. This is more typical of what we see of lasers. It's caused by relativistic beaming. So I guess takeaway from this is that we do think, I think this helps confirm that most of the sources are consistent with being young. And we've really got maybe 1 or 2 interlopers that might be beamed. See, I've got here a source age estimate. So this is an example. So I've got an example of one of the radio spectra here. This is a plot showing the turnover frequency. The turnover frequency is just where it goes from optically thick to thin versus the linear size. And it turns out that most AGN, they fall on they have a scaling relation here. It also has an analytical basis that you can calculate. Scatter is mostly due to just measurement uncertainties, or possibly like the environment of the source influencing its evolution. But anyway, most of our sources, if you take a typical spectral peak of 15 gigahertz, convert to the rest frame of 40 gigahertz, and assume a speed, here I assumed 0.1 c. If you do very simple math, which I like because this makes sense, you find you can get an age estimate of 30 to 300 years. I'm sorry, that is based on a size estimate from this plot here. Sorry, I'm realizing how many slides I have left. I'm panicking slightly. Okay. But all right, we're on to some new stuff that I really want to show you guys, so it's good. These are some new insights on jet lifetimes triggering engine cycles. I've been talking about the VLAS first comparison for a few years now, but I want to get into some new stuff. And actually, I'm going to do this slide, and then we're going to go more into the triggering. All right, so this is actually the last thing I want to show you from my 2020 paper, and it's that we did some simple back of the envelope math to figure out, like, are we seeing the number, like, is the number of newborn jets we're finding consistent with basic expectations for radio AGN lifetimes. So we found the sky density. We focused just on the type 1s versus we had 13 type 1 quasars in 3,400 square degrees. So again, you can do some very simple math and get a sky density. If you think about like how many would we expect, SDSS and FIRST found about 1 radio loud quasar per square degree. You assume the sources typically live to be about 1 million years, and you ask how many would we have caught within 10 years of switching on. We actually find that this sky density here is 400 times more than we would expect based on that. So that tells you that there's something wrong about those assumptions. And what we argue in the paper is that sources tend to have a shorter period of occurrence, and they tend to be be more short-lived. And perhaps small jets or short episodes of jet activity might actually have an impact on galaxies, although it can be a bit subtle and challenging to measure operationally still. Sorry, I'm flying through here so fast. If anyone has any questions, interrupt me. Okay, so I want to show you some Hubble Space Telescope follow-up that we've done. This is a graphic that kind of illustrates what we did with first in VLAS. We took data from the 90s, or upper limits of first in the 90s that were detected 20 years later with VLAS. But from like a press release that's a little bit too dramatic, maybe. I don't see any noise in this. But you can just believe me. Really are intriguing. And really interesting to know like what host galaxies and these sources look like. And so I was able to get some HST time for a pilot study to investigate this. So we obtained some WIF-C3 near-infrared imaging. And I was very fortunate to have a fantastic student from the Naval Academy, Midshipman Olivia Achenbach, work on this data with me over the past 2 years. And she gave a press conference, actually, at the AAS in January of 2025 on this. So here are some of the images that Olivia has been working on. So we got time on. I was perhaps too conservative. I asked for 4 orbits to look at 4 of the newborn jet candidates. I wish I had just asked for all of them. But anyway, these are the 4 we started with. The one on the left here and the one in the middle here, these are really interesting because they're at lower redshifts. Redshift of 0.6, redshift of 0.2. These guys are a little farther away, so you don't see as much. But I'm going to focus in on this source here. So the goal is to do some quasar host decomposition. This is a fun graphic that Olivia made explaining the process of quasar host decomposition, including modeling point spread function or PSF, subtracting that from the image to obtain a model that we can then fit a surface brightness profile to. So this is just showing, this is an initial residual with a very simple stair-stitch model that kind of helped alert us to the fact that this system might be interesting. We then went back and did some more detailed modeling with GalFit. In this residual over here, you can see we have some spiral structure left over. There's this beautiful tail. There's this tidal companion here. And there's also this crazy looking ring galaxy here. So you might be wondering about the redshifts of some of these things, including this ring galaxy. I briefly thought this might be like a collisional ring galaxy where this source here went through and then interacted with this quasar host. But we did some follow-up with Gemini, where we put the slit not through the quasar, or we already know it's rich, I'll be on it, but we put it through the tidal companion and through the ring galaxy. And long story short, the ring galaxy, the tidal companion matches the quasar redshift, but the ring galaxy is in the foreground. We also were able to use this data to do a little bit of simple kinematics. So we used we were able to measure an offset velocity between the companion and the quasar, and make some big assumptions on where that companion might have initially started, say 50 kiloparsecs away. This interaction time scale, producing this tidally disrupted material here. We also saw extended emission, oxygen emission between the host and the tidal companion. This is work that my colleague Mark Lacey assisted with, since I am not a spectroscopy expert. But what that told us actually is that This source has a quasar ionization echo, which is really cool. This is a nice cartoon of a famous quasar ionization echo called Hang's Forewarp. So basically, this is when you have a quasar that ionizes some gas, and that ionized gas shines for a while, and gives us a time scale of when the burst of AGN activity happened. So again, doing very, very simple math, measuring the extent of the extended oxygen-3, 50 kiloparsecs, we were able to estimate that the bursts were done over 5 years ago. This is all. This is a paper that I have almost completed. We need to polish up some details about the GalFit modeling and polish up some of the spectroscopy that hopefully it will be out later this year. All right, so getting close to the end here. I did want to mention something about duty cycles as well. So the duty cycle of an AGN is the fraction of time that the AGN is radio loud compared to its total lifetime. So these are some follow-up images of a subset of the newborn jets from my 2020 paper. And so these are low-frequency radio images from LOFAR, the low-frequency array, at 144 megahertz. And so we were lucky that several of them were included in the lots the LOFAR 2-meter sky survey data release. And the cool thing is we found that a number of them were detected. Where's my favorite one? So this is the one that I've been focusing on that has the ionization echo. And it has some interesting extended LOFAR emission. And so here's a better image of the LOFAR emission. So this is the HST image, contours of the LOFAR lots data at 144 megahertz. And then this points to the location of the newborn jet. So it turns out this source is actually a restarted radio quasar. These large-scale 240 kiloparsec lobes, they're actually from a previous jet outburst. So this gave us another timeline for this source. We were able to, just based on some constraints, very simple constraints. So we use these papers listed down here. If any of you are doing similar work and are interested, we were able to very roughly constrain the source age to 10 to the 7, 10 to the 8 years. This would be a good source to do a spectral aging study on, but we would need more low frequency data. So this gives us kind of a timeline for this source. And so I've listed out everything here. There was a tidal interaction a billion years ago. There was an initial radio loud phase 10 to the 7 to 10 to the 8 years ago. They united 100,000 years ago, and then 10 years ago, measured on the Earth, a new radio loud phase began. And so the key takeaway, a lot of details here. The key takeaway is that so-called radio quiet and radio loud quasar activity in this source has been intermittent for a significant fraction of the source's lifetime. So my student, Olivia Achenbach, she wanted to make a cool graphic of all of this for her press release talk at AAS last year. And so this is what we came up with. You start with the triggering catalyst, like a minor merger. The jet then forms, and you have this interesting, this young and compact phase where the jet is confined within the lobes. Still, exploring the time in between phases, but 10 to the 7 to 10 to the 8 years later, those lobes faded and be only detectable at low frequencies, and then the source has a chance to perhaps be re-triggered again. If only we could do this for like 1 million radio AGN, we would we would really understand their life cycles. This is just one source. We need big volume limited studies of this. It could be possible with current data. I talked with a couple of you about that. Yeah, it's also going to be really important going forward in the future. So I want to just, so I'm running out of time here, just emphasize that, let me skip ahead here. We've got a lot of really cool new and future multi-wavelength surveys that we can combine with VLAS to better understand radio sources, especially AGN that are known. So yeah, in the imaging domain, we've got Euclid and Roman coming. Spectroscopic domain, we've got DESI, also moons, and then of course in the time domain, we have the LSST, which has just started ramping up, and it's going to be really exciting going forward. Sorry, one more quick thing. This got out of order. I do want to also just make a quick plug for another one of my students, midshipman Jack Ray, also from the Naval Academy. He's been working on statistics of VLAS source variability. He has created and vetted a 3-epoch VLAS catalog. And so he's going to be, he presented this initial catalog at the recent AAS Phoenix, and he'll be ramping up with a whole bunch of science follow-up on this in his senior year next fall. So yeah. There's my summary. We've learned, the main takeaway, if you remember nothing else, is that we think that radio disks are intermittent, and that matters for understanding jet triggering and how they connect back to galaxy evolution. And there's lots of cool surveys to come. So I've left my email addresses on here. My email address tends to change a lot at these Navy institutions. But if you Google my name, you should be able to find me on LinkedIn, just in case it changes. So yeah, I'm happy to take any questions that you have. And thank you again for your time.
What a surprise.
So throughout this talk, you mentioned about spectral variability and showed the peak spectrum sources. One thing you can do with those is you can age the synchrotron emission. In addition, you've also talked about pneumatically aging the radio emission in other ways than through the spectrum. So have you gone through and compared those ages and tried to test like synchrotron emission models and drawn out the magnetic field and sort of tested to see if those are correct?
Yeah, so yeah, I mentioned a couple of things there. So with the spectral aging models, yeah, Jeremy Harwood, the software package, he used to be my office mate at Astron. So I'm quite familiar with how that works. The models that he uses in BRATS are designed, they're the classic models designed for like giant radio lobes that are aging like in the intercluster medium. So I think some additional energy loss mechanisms would be needed. ISM scales, but it could still be worth trying. The main thing it requires is measurements at a lot of different frequencies. But yeah, good point. It is cool to actually get ages from that. Be a next step.
Could you go back to your simulation slide that you showed close to the beginning?
Yeah, sure. Did you have a particular question about it?
Yeah, but I just wanted to check that I'm getting the numbers right. Yeah, so I guess kind of my question is like, for the lower jet power and the higher jet power simulations, why were those run over different periods of time? I guess like what would the figure on the very right look like?
So the author, Dipanjan Mukherjee, so I believe he ran them to reach like similar extents. So I should have explained what all the axes were. So this is kiloparsecs on this axis, also kiloparsecs here. Then the color scale is gas density, and so he ran them to be few kiloparsecs. It just took this one longer to get to that size. Another way it could have been to run them for the same amount of time and show that one is slightly more extended than the other. But yeah, I chose to show it this way. Good question.
Were you requiring that all your new things in VLAS were quasars, or it just happened to be that way?
That was a requirement. So there have been some other papers out looking at variability within VLAS epochs, and then variability between VLAS and first or other surveys. And different groups have chosen to do this part differently, do different science, and there's still more ways to do that. So yeah, we did require that they were in the latest SDSS Paris et al. Quasar catalog. And then for WISE, we used the OSIF et al. 2018 catalog. So we used both SDSS and WISE so that we captured both the type 1 and type 2 systems. Yeah. Does that answer your question?
Or just like other galaxies, right? Like
yeah. So other people have.
So yeah.
Exactly. Other people have done that. This was just kind of like a low-hanging, simple study. Since a colleague of mine, Decker French, she has a really nice paper that came out last year that I was not able to fit into this talk, but she compared first to VLAS for a sample of post-starburst galaxies, and she found some interesting variable sources that way. There are other populations you could look at. I think there have been 1 or 2 other studies with variations on this approach as well. Yeah. You can also look, now that we have like 3.5 epochs of VLAS, you can look within VLAS. So.
You plan on expanding to like racks, using like the racks low, mid, and high to sort of constrain variability, like new variability?
Yeah, that's a good question. So yeah, so RACS, the Rapid All Sky Continuum Survey. It's a survey being done by a telescope that's based in Australia, Australia Square Kilometer Array, half a kilometer. But yeah, it's in the process of conducting a number of surveys. It also has its own dedicated time domain survey called VAST. The VAST, it's similar to VLAS in a lot of ways, but it has a the cadence or the time between epochs is a little bit shorter than VLAS, but it covers a smaller area of the sky. It's a trade-off. But they have been ramping up a lot, and there'd be a flurry of papers. Yeah, I don't know that the VAST data are public.
Not yet, at least.
Yeah, I don't believe they are. I think they're still in the relatively early stages. I don't think they've taken all their observations yet.
Yeah, so I'm very much excited about the
Yeah.
resolution. So my question is like,
Synchrotron emission. Sorry, do you mean? Am I going the right way? Do you mean the lifetime plot that showed that where I made the point that we see them then?
No, like I'm talking about the overall diffused synchrotron emission.
Oh, diffuse like oh, I see what you're saying. Yeah, galactic foregrounds. Yeah.
Are there plans for doing these kind of
So,
categorization
with VLAS?
Yes.
That's a good question. So it is possible. VLAS is actually not the best tool for galactic foregrounds because it's high resolution. So it resolves out a significant part of the diffuse foreground. But you still do capture some galactic foreground emission. I think where it's going to be most prominent is going to be in polarization. So VLAS, in addition to being a time domain survey, is also a full polarization survey. Those data products are not available yet. It's going to be a few years.
Slowly.
Yes, very slowly. But from what preliminary studies have been done on looking at rotation measure. Polarization angle is changing with frequency. And it can tell you about, whether it's a foreground or intrinsic polarized emission, that there is a contribution from the Milky Way. I think that there are some other full polarization radio surveys like POSSUM that will probably be more optimized for this. But I'm sure there will be some papers written down the line using VLAS. VLAS is going to keep giving more products are slowly rolled out.
Let's thank Kristina again. Any discussion, questions? I think Sarah is in charge of.
It's half an hour.
Yeah.
Just more.